So now let me do some more calculations with this so that we understand this circuit better. Let me draw only the small signal picture. The current source is open and all of them are short. Okay. Let's try to understand what is the effective resistance looking into different nodes in the circuit. That will give you a better understanding of the circuit. So how many nodes are there here in the circuit, excluding the ground? Excluding the small signal ground, how many nodes are there in the circuit? 1, 2, 3, 4, 5. Okay, this is one node, second node, and is there any other node? That's all, only 3 nodes. So let's quickly find the resistance looking into each node so that you also get the feel for doing small signal calculation and we also better understand the circuit. Let's start with the simplest thing. So let's look at the resistance at the output side. What is that? We already calculated. R0 of M2 in parallel with R0 of M4. But again, if I write the down resistance, how much was this? It was actually 2 times R0 of M2. So then what is the up resistance? 2 times R02 parallel with, I mean, this is something we derived already. I'm just writing it for the sake of completeness, right? No new calculation here. So now let's look at the other 2 nodes. So oops. Fine. Let's start with node A. I'm trying to find the effective resistance looking into this node. What will I do? How will I find it? Same thing. I mean, it's not a trick question. You apply a test voltage and find the test current, or apply a test current and find the test voltage. Doesn't matter. Okay. So now tell me, I have a test current I test here. So obviously this is going to split in both the branches. Now do you think the current flowing on the left side will be higher or the right side will be higher? Why? Why VGS is 0? Yeah. Again, this is again the same symmetry argument, I mean asymmetry argument we started with. Although this is asymmetric, provided I have the same VGS on both ends, by contradiction I can show that the 2 currents have to be equal and these 2 voltages have to be equal. Correct? So once again I have the 2 nodes to be at the same potentials. What can we do? We can short them silently. So once again this becomes a half circuit. So now we can reduce this. So we quickly draw. This is 2x of M4. This is 2x of M2. And here is where you are applying the test voltage. Okay. So now you should be able to tell me directly what is the resistance looking into the source here. Resistance looking into the source, how much is it? Yeah, 1 by GM. I have 2 of them in parallel. But I can say that the resistance looking into the source is 1 by GM, provided what? Or, I mean, that's a very, I mean, much small. R0 is much larger than which resistance? I mean, yeah, the effective resistance at the drain, right? So what is the resistance at the drain here? That's 1 by 2 GM4, right? As long as this drain resistance is much smaller than the R0 of the transistor, and here the R0 is R0 2 by 2, we can make the statement, and this typically is fine. Typically GM times R0 is much greater than 1, so even between multiple transistors we can generally make this statement. that 1 by Gm of some transistor can be ignored compared to R naught of another transistor. It's a reasonable assumption to make in practice. So which means the resistance looking into the node A is approximately 1 by 2 Gm2. So again, please note I am not writing KCL anywhere. We are trying to get the results by inspection and by reusing some results that we already know. So unless until required, we will not use KCL. Think of KCL as having AK-47. You don't use AK-47 to kill mosquitoes, right? Mosquitoes, you just do this and it's gone. Use it when it's required. Okay, so now we looked at the output node, we looked at the node A, then let's look at the pending node. Great. So we are now interested to find the resistance looking into the node B. So once again, what will I do? Yeah, same thing, test voltage and find the test current. This is V-test and I'll find how much is the current drawn. But if you were to take a guess of what the resistance is, what would be your guess? 1 by Gm of this transistor. Why do you say that? Because of this direct connection you are saying. Right? Yeah, it is very tempting to say that this resistance is 1 by Gm, but let's actually find out. So I am applying the test voltage here. So same test voltage is applied at the gate. So let me write it here. So again, let me actually see if I can make some space. So for small signals, I can treat it as a voltage controlled current source in parallel to R0. Correct. So if I were to write my test current, that will be sum of these two currents. And what is the value of the current source? Gm 3 times the test voltage. Gm VGS, right? The VG is the test voltage. Source is 0. And what is the current through R0? Plus Vt by R0 3. And again, for all practical purposes, I can assume that this is smaller compared to Gm Vt because R0 is much larger. So it's very tempting to say it is this. But remember that the test voltage Vtest is not only the gate voltage for M3 but also for M4. So which means even M4 will behave the same way. So we'll once again have a current source and R0 for M4, and I'll say M3, M4 are identical. So this current will also be Gm3 times Vtest. This is fine. So now because of this test voltage Vtest applied to the transistor M4, you will have a current being pushed out here, and this current can either flow through R04 or it can flow down. There will be a current split between these two resistances, and whatever current flows down will have to come like this. Does it make sense? I mean, what I am saying is I have a current Gm 3 times Vtest. This current will obviously, some part of it will flow through R04. The remaining will basically flow down, and that will basically add up to your test current. Right? So how will you find what fraction of this current flows down? I mean flows here. What is? Yeah, I mean it's basically a current division between the resistance R04 and whatever resistance I have looking down, right? And what is the resistance looking down? We just computed, 2 times R02. So in addition to this current, we will also have this additional current of Gm 3 times Vtest. And what fraction of this current will flow down? What is the current division factor? R04 by? So I have this current. I am trying to find the division between these two resistances. So current flowing through the down resistance to R02 is this current division factor. Is this clear what we are doing? So which means my total test current is going to be roughly approximately, again I am ignoring R0 everywhere, so this is GM3 times 1 plus R04 by R04 plus 2 R02 times V test. So what is my effective resistance at the node B? It's 1 by GM3 times this factor. This is okay? So in fact you can take it as an exercise. Please calculate the up and down resistances separately, like how we did it in the last class. You will find that looking up the resistance is basically this 1 by GM, because you will have this diode connection. You will find the resistance looking down is approximately this additional factor. Okay. So again I'll give it as an exercise. So you find what is the up and down resistances explicitly the same way we discussed in the last class. So now look at this expression here. So let us say I make, for example, R04 to be infinity. That is, I have a special case where the R0 of the PMOS transistors is really large. How will this simplify to? R04 is very large, tending to infinity. How will this simplify to? It will become 1 by 2 GM3. Right? So in fact, you see that, I mean, under some very special cases, this is not just 1 by GM, it can be 1 by 2 GM. Okay.